All right, this is a video on the reciprocal function family in Algebra 2. We'll start off with an introduction and then do a few solved examples. Really what this video is addressing is graphing some basic rational functions where we'll be looking at some vertical stretches and vertical reflections of rational functions and also thinking about shifting or translating them in both the x or the y dimension. And so we'll look at some examples of those. Our parent function is probably the most important one to just really think about. This is where all other rational functions are derived from. Y is equal to 1 over x. Okay, and so I'll go ahead and graph that parent function right now and plot some points by hand and give you a sense of what that function looks like. So, and I guess the way I want to think about that is just by plugging in different values of x to see what y would be. So if x is 1, 1 over 1 is 1. If x is 2, y is a half. If x is 3, y is a third. If x is 4, y is a quarter. You can also think about what if x were to be a half? What's 1 over a half? That would be 2. What's 1 over a third? That would be 3. And so you're getting a pattern that looks something like this. And we're going to have both the x and the y-axis would be asymptotes here. Reminder that asymptotes are lines that a function would approach, get infinitely close to, but never actually intersect. If x were to be negative, 1 over negative 1 is negative 1. 1 over negative 2 is negative a half. 1 over negative 3 is negative a third, etc. And we can do the same thing for fractional values of x that are less than 0. And we'll get a symmetric pattern here. So that is the core graph, the parent function graph, the most important graph for rational functions we'll be working with. I don't know if this is mathematically precise, but I think of this graph as what I call having two arms. Okay, it has this arm in quadrant 1 and this second arm in quadrant 2. This is a non-continuous graph. Those graphs do not intersect. Okay, those graphs, you can think of the two arms as having a gap essentially between them at x equals 0. Okay, so they do not connect. I mean, they don't. So they are non-continuous. Both x and y axes are asymptotes here, and again, our curves will get closer and closer to those axes, but never touch. For a domain in a range, it's important to see that for a domain, x is simply not equal to 0, but all other real numbers are allowed. And for a range, similarly, y is not equal to 0. Okay, this function is undefined for x or y equal to 0. Standard form, which we'll do a little bit of practice in a little bit, is this example right here. So it's a little more generalized standard form. The a acts as a vertical stretch or a vertical reflection. So let me write that down here. So the a acts as a vertical stretch, in other words, a multiplier, or a vertical compression if a is less than 1. If a is negative, that can act to vertically reflect the graph across the x-axis. Here's what h does. The vertical line x equals h is a vertical asymptote. Okay, so if h were 2, the denominator in our rational function would be x minus 2, and that line x equal to 2 would be a vertical asymptote. And I hope you can see why that makes sense. If x is equal to h, we would have a 0 in the denominator of our equation. And k, that line y equals k is a horizontal asymptote. You can think of that as simply being a vertical translation, a movement in the vertical direction from the x-axis up or down, okay, depending on what k is. Let's look at some examples here. So for graphing, let's do a graph of y equals 3 over x. So what you might want to do is just as you get familiar with these, let me just adjust my axes real quick. As you get familiar with these, you won't need to graph the parent function, but I think it's often valuable to graph the parent function y equals x. something that looks like that. Remember, it goes through the 1, 1 point, and the -1, -1 point. So that would be the line y equals x that I just graphed. And I will just color coordinate that. That's a, excuse me, not y equals x, y equals 1 over x is the parent function I just graphed, and that's what's in black. Let me graph y equals 3 over x in red. Okay, and I think you can see that that's just a vertically stretched version of our parent function. Every y value is being multiplied by 3. So if x is 1, y is going to be 3. If x is 2, y is going to be 3 halves. And if x is 3, y is going to be 1. Okay, so I hope you can see that pattern right there, and we can continue that graph like so. And that's going to happen in the quadrant 3 as well. If x is -1, y is going to be -3. If x is -2, y is going to be -3 halves. And then this value as well. If x is -3, y will be -1. And so we can plot that there. So that's the x. That's the graph of y equals 3 over x. I can throw in some values here into our table. If x is -3, y is -1, -3 halves, and -3, and 0 will be undefined. If x is 1, y will be 3. If x is 2, y would be 3 halves. And if x is 3, y would be 1. So we're just plotting points and verifying that we have a vertical stretch happening here. I want to show you how you can graph some of these on Desmos, and then just address some of these without having to graph these by hand. So y equals 1 over x, you can see, is our parent function right here in red. That's our standard parent function. And then in green, I think you can see that vertical stretch that we just did, a different example of, but the same thing is happening here, where the graph is somewhat moving away from the origin, moving away from the x and y axes, and just getting stretched. Similarly in purple here, if we're multiplying our 1 over x parent function by a value less than 1, in this case 0.25, we'll have a vertical compression, and we'll get a function that is just compressed closer and closer to the origin, closer and closer to the axes. And then the big thing to see here is this negative sign for this last one, y equals -6 over x. So we have a vertical reflection across the x-axis, and additionally we have a vertical stretch 6 times by a factor of 6. And hopefully it's obvious that's this graph right here. Okay, and in all cases, the domain is all real numbers except for x equals to 0. Okay, these functions are all undefined for x equal to 0. What if we want to do a translation or a shift in the vertical or horizontal dimension? We can look at something like this, where we have h and k being involved now, as we looked at earlier. I'm actually going to rewrite this function a little bit differently. Okay, I like to think about forcing there to be a subtraction in the denominator there. So really we can see that the value of h itself is -1, okay? X minus a -1. So h is -1, k is -2. So our vertical asymptote is going to be at x equal to -1. And our horizontal asymptote is going to be at y equal to -2. We can almost think of this as our new origin. If we were to simply graph y equals 1 over x now, based on that new origin, we'd have a correct graph of the function. Okay, so remember some of these key points we have. Over 1 up 1 from our origin, over 2 up a half, over 2 up a half, over 3 up a third, and then symmetrically around that. And then in the opposing quadrant as well. Okay, so that would be our graph of our translated transform function. I will erase away our asymptotes for a moment just to confirm that that's what the graph looks like based on the true set of axes, the true set of x and y axes. But it is nice to have the actual asymptotes listed in as well. Okay, just keep in mind those asymptotes are not our axes, right? And then lastly, we can think about, can we write an equation here? Can we find an equation for a particular function? So what I like to do when we're doing these sorts of problems, I like to draw in what it looks like the asymptote is first. So it looks like that asymptote is at x equals -3, that vertical asymptote, and it looks like this y asymptote. Let's get that a little more precise here, is at, what is that at? Y equal 4. Okay. And so those are the values of h and k, so we can throw that into our equation, and we still need to think about what a is. It looks like this function has been stretched vertically. Okay, so we have y equals a over x minus a -3 and then plus a 4. Okay, to think about what a is, I'm going to highlight this zone right in here and particularly be thinking about these couple points. I'm going to imagine that that's my origin. Okay, so I want to just sort of imagine that and think of this as over 1 over 2 and up 1 up 2. So this is a 2, 1 point with my modified origin, and this is a 1, 2 point. I hope you can see, based on the work we've done with inverse variation so far, that a would be 2 in this case. Okay, you can see if x is 2, y would be 1, and if x is 1, y would be 2. So if we're thinking about just the core form of inverse variation, and that could have been a k instead of an a. You know, in a prior video we used k, but in this case, if we plug in a 2 for a, our points work out. So I am going to do that and plug in a 2 there, and that would be the equation of the graph that we've been given. All right, and that's a good place to stop.